Hello again, and welcome back to YCP Chemistry Labs, your College of Pennsylvania's YouTube channel dedicated to getting you ready for General Chemistry Lab each week. This week in the General Chemistry 2 curriculum, we're getting ready for the kinetics of a crystal violet reaction experiment. Now, depending on where you're at in lecture and which day of the week you have lab, you may or may not have yet discussed some of the concepts, the theoretical concepts that underlie this week's experiment. So I'm prepared to give you a little more background information than usual this week, just to make sure you're ready and understand what you're going to be doing as part of the lab. So not only will I walk you through what you're going to do in lab, but I'll provide a little bit of information to help guide you on the analysis of your data that you collect, so that you are ready to successfully determine the rate law of a reaction. And that's what we're after today, or this week, is the equation or a mathematical expression that tells us how fast a reaction is occurring. We could look at a lot of different reactions, but we're going to look at one that occurs between a dye known as crystal violet dye and the hydroxide ion, which will be delivered from sodium hydroxide, or come to our reaction by sodium hydroxide. So the word rate, there's nothing particularly scientific about that. We have lots of different rates in our lives, so we should be familiar with that word. It's just referring to how fast something happens. But a rate law in chemistry is a mathematical equation that allows you to predict how fast something occurs based on three things, really. What is the concentration of the chemical that's at work in your reaction? What is what we call the order of that chemical, of that reactant? And what is the rate constant, which is really more of a proportionality constant, but it's dependent upon some of the things that are happening at the molecular level. When we put these three things together for a generic reaction, for example, X turning into Y, the rate would equal K, the rate constant. So that's what this generic letter K is. That's our rate constant. Always we use K to represent the rate constant. Concentration of X, that's what the brackets universally represent in kinetics, is the concentration of the chemical in the brackets. And then N is the order that I'm referring to. What N is indicating is that not all reactions are a one-to-one response. In other words, the rate doesn't always directly or linearly depend on the concentration. It might be that your reaction is 0, first, or second order. Those are the three most common orders, although not the only orders that reactions can be. But if something was 0 order, if we plugged in the exponent 0 right here, this term would actually disappear and the rate would just equal the rate constant, which is a constant. So the reaction speed would not change over time. When a reaction is first order, if you plug in 1 here for the exponent, rate equals the rate constant times the concentration. So that's now a direct linear relationship between the speed and the amount. And as the amount of reactants decreases, the speed of the reaction also decreases. It keeps pace with that. If a reaction is second order, if you plug in a 2 here, the speed of the reaction depends on the square of that concentration. So now as the amount of reactants decreases during the progress of the reaction, when you square that number, it's going to get smaller very quickly, and so your speed is going to slow down. All right? So that's the effect of the order of the reaction. Now, if you had multiple reactants, instead of just X turning into Y, if you had two things that had to react, A plus B, for example, each would be reflected in the rate law with its own respective, potentially unique order. This is the case in today's reaction, where we're going to have crystal violet collide with hydroxide ions, so each is going to need their order. I'll come back to that in a little bit. But regardless of what the reaction is, if you're going to observe how fast any reaction is, you need some observable, literally something you can see or observe changing during the reaction. So some of the common variables that chemists use are measuring pressures during a reaction involving gases. You could see those fluctuate. Measuring concentration, that's what we're going to use today. Perhaps measuring temperature, if you understand how the temperature is going to be changing in relation to the amounts of chemicals, or the speed of the reaction. So let's look at this reaction today with crystal violet and hydroxide. What we're going to be able to see changing is the color of the reaction. And I very purposefully today wore this nice purple shirt that I have on and a purple tie to go along with it, because the chemical crystal violet is a purple colored dye. And the more dye that's present, the deeper the purple color is in solution. And so while your reaction occurs today, you'll literally see your system start with a nice deep purple color like my tie. But over time, as the dye molecules react with hydroxide ion molecules, they will bond together, just like me putting these two pens together, and the new product is no longer purple in color. And so that purple color will fade from the very rich, deep purple to a lighter shade of purple like my shirt. And eventually, if we let it go long enough, it would completely disappear when the reaction had reached completion. So we have an observable in the color. Now, we've looked at color before, and we've used UV vis spectrometry to measure the amount of a chemical based on the color. So today's reaction, you will have it take place in a little cuvette in your spectrometer. And you will insert your solution into the spectrometer. Now this is blue, but it'll be purple in the actual lab. We'll put the spectrometer we'll put the cuvette into the spectrometer, and we'll measure how much light is coming through. So the absorbance of the solution is directly related to the concentration of dye in the solution. And so if we were watching this over time, the absorbance would be very high at the start, and then it would drop off over time. So it would have a shape very much like that. Now, this is a fairly complicated situation, because we have not only dye, but hydroxide ions that are contributing to how fast the reaction is. The spectrometer is going to only measure the amount of dye that's present, though. And yet our overall rate law is going to depend on not only the dye's concentration and what its order is, but the hydroxide ion concentration and what its order is. Now we have two variables then, two unknowns right now, actually a third, because we don't know the rate constant either. It's a pretty complicated scenario. So we're going to help and streamline things a little bit. The dye is first order. So M is equal to 1, meaning it's first order. For any reaction that is first order, this shape that we've seen right here, this decline, notice it's not linear, it's curved, right? But the natural logarithm of the concentration, or absorbance, because absorbance is directly related to concentration, so they behave the same way. So over time, the natural logarithm is linear versus time. So this exact same data set, if I just took the ln of each of these values and replotted them versus time, it becomes a straight line. All right. This is borne out, as you see in lecture and start to learn these topics, in what we call the integrated rate law, that says that the ln of the concentration of a reactant is equal to the ln of the initial concentration of that reactant minus kT. This looks an awful lot like a y equals b plus mx equation, like we sort of did with our Clausius-Clapeyron stuff earlier this semester. So y is my ln of concentration or absorbance, which is a stunt double, so to speak, for concentration because they're directly linked. X is time. That means that the slope of a graph of ln of absorbance versus time, that means that the slope is related to the rate constant. And so the slope m is equal to negative the rate constant. But the trick here is, what about the hydroxide ion? Because the hydroxide ion is part of this system as well. So let's shift gears for a second and imagine that you or I was invited to go shopping with somebody really, really wealthy, like Bill Gates or Warren Buffett. The caveat, though, is that for every dollar they spend, we have to spend $1. On a shopping spree with a really wealthy partner like Bill Gates or Warren Buffett, but we had to spend dollar for dollar what they do, we would consume all of our money very quickly. And we would definitely notice a change in the amount of money we had left. You know, if I started with a pile of money, it would very quickly disappear. But the pile of money that a Bill Gates or Warren Buffett has is enormous. And even taking off the little tiny bit that I've spent, them matching me, they'll still have an enormous pile, still billions of dollars, right? So their amount would be essentially unchanged. So we do something similar to that in chemistry when we have two variables that might potentially affect our outcome. We're going to make this a huge concentration, just like Warren Buffett having billions of dollars. So over the progress of the reaction, it's going to stay essentially constant. It's still going to be a huge amount at the end. Meanwhile, our dye, being a small amount, will be entirely consumed over the progress of the reaction, like you or I spending all of our money. And so if it's a constant, we can just group it together with the other constant, K, and call it K prime. All right? And then what's left is the dye raised to its order, which we already said is first. So what we're going to be after then, and this would change then to K prime down here as well. So what we want in today's lab is to gather absorbance values at a number of different times so that we can find this, quote, pseudo or temporary rate constant for this reaction. And then we'll do it at two different concentrations of the hydroxide ion, and I'll show you how we can use that information to find the unknown order of the hydroxide ion. Okay? But once we find our K prime then, K prime is going to equal negative the slope of our reaction. For two separate trials of data then, from the first trial, K prime 1 equals the true rate constant times the concentration of hydroxide raised to its order that you used in the first trial of the reaction. When you repeat this for a second reaction, okay, your second reaction will not have as steep of a slope, you'll see. So you will get a different number for K prime in the second trial of the reaction. But that second K prime is again the true rate constant times the hydroxide ion concentration that you used in that second trial. So now we have two equations with two unknowns. Those unknowns being the true rate constant K and the order of hydroxide. You will know the concentration of hydroxide because you will measure the amount that you use during your reaction. And you will know these two values because they are the slopes of your two graphs that you had. You could set up and solve then by taking K1 prime divided by K2 prime equals K OH to the N1 K OH to the N2. Well, K, I don't know what it is, but K divided by K will reduce. This will be a numerical value. You'll get some number over here. And these can be combined using a special rule of exponents. You can gather them into one expression raised to a single exponent. All right? And that'll be hydroxide ion concentration of the first divided by hydroxide ion concentration of the second. This expression should come out to look like something pretty easy to solve. By easy to solve, for example, it might be something like 3 equals 3 to the nth power, or something really close to that. Maybe it would be something like 4 equals 2 to the nth power. In this first case, n would equal 1, right? Because 3 raised to the first power equals 3. In the second case, n would equal 2, because 2 raised to the second power equals 4. Now they might not be perfect numbers, so if you got like a 3.87 equaled 2 to the nth power, I would say n is approximately equal to 2 in that case, because that's a lot closer to squared than 2 to the first power. And our orders must be whole numbers. So that's down the road. That's part of your analysis that you'll do after the lab. Okay? To get K then, this is how we get n. To get K, you simply come back in with your n value and substitute into either of these equations and solve for the K, because that will now be the only unknown value once you know what n is. Right? Okay, so let's talk about the specifics of the procedure then. It's pretty straightforward. The data that we're collecting is going to be used to make these graphs that I'm erasing right now. You're going to generate data for absorbance of your solution versus time. You want to keep track of that time in seconds or minutes. If you gather it in minutes, you'll want to convert it to seconds for your graph. To make your graph, though, you're going to plot the ln of the absorbance values versus time. And you'll do this for 2 trials. So you should have data that's set up pretty similarly for your 2 trials so that you get 2 graphs. All right. And as I already indicated, the first one will be a steeper slope than the second one. That's because we're using more hydroxide in the first reaction, and so it will happen a lot faster. All right, so that'll be what we keep track of. Other things that you need to record, as indicated in your lab manual, are the concentrations of particularly the hydroxide ion and how much you added to the reaction so that you can calculate the concentration of hydroxide once the reaction is mixed. And that is done using the standard dilution rule that we've learned how to use in Chemistry 1. All right? All right. So we're ready to consider the 3 pre-lab questions that we have for today's exercise. The first pre-lab question asks us, or gives us some information about a graph that was made. And in this graph, we're told that a plot of concentration versus time is linear, or a straight line. So each order of reaction has a different variable that will be directly related to time, or linearly responsive to time. For a zero order reaction, or a zero order rate law, that's going to be concentration that would give you a straight line versus time. For a first order reaction, like we were talking about earlier, our crystal violet, that's going to be ln of concentration versus time that produces the straight line. And for a second order reaction, it's actually the reciprocal of concentration that will produce a straight line versus time. In each of those cases, one of the reasons we would make this graph is because all 3 of these forms here are very much like a y equals mx plus b, when x is the time variable. And there's something different on the y-axis in each of these 3 cases. But what's really important about this is not only one can be true. A reaction can only have one order for its reactant. So you would identify which pattern was true, but then you get the bonus information of the slope being related to the rate constant, like I was describing earlier for our analysis of our crystal violet reaction. So for this case, you're told that it's the plot of concentration versus time. So this tells you what the order of the reaction is. And then the slope is hinted at. It's given to you numerically what it is, 2.15. So negative 2.15, I should say. So you can figure out what the rate constant is from that information. In the second reaction, or second problem, sorry, we are looking at a decomposition reaction that we're told is first order. So since it's first order, the natural logarithm of the cyclobutane in this case, its natural logarithm of its concentration equals the natural logarithm of the initial, that's what these little zeros always mean, concentration, minus k, the rate constant, multiplied by the amount of time. So we'd like to figure out how much cyclobutane is left after 2 minutes of reaction. So that's a sneaky little twist in this problem, because the ln of the amount of cyclobutane is going to equal the ln of the initial amount, 2 molar, minus, we're told the rate constant's this 0.015 reciprocal seconds, but we can't put 2 minutes in here. We have to put 120 seconds so that our time units cancel each other out. And you would get this to equal negative 1.107. So that clearly can't be the concentration of cyclobutane, because anything's concentration can never drop below 0. But that's not what our equation says, is it? Our equation says this is the natural logarithm of the concentration. So the concentration would be found by using the natural exponent, e to the negative 1.107. So I'll leave that to you to calculate, and don't forget to put on the units that would be appropriate for the concentration. The third question talks about a second order reaction, and it asks us to determine the half-life. The half-life is a quick way to describe how fast or slow a reaction is by saying how long does it take to use up 1/2 of the initial concentration of your chemical, your reactant. that relationship between time, half-life time, that amount of time, and how much you start with is different or unique for each of the three orders that we've been looking at here. So I've quickly put them up here. For a zero order reaction, the half-life, the amount of time, is directly dependent on how much you start with. For a first order reaction, interestingly, it actually doesn't even matter how much you start with. It's just the ln of 2 divided by the rate constant k. And for a second order reaction, the one we're interested in this case, the half-life, the amount of time to use up half of our initial chemical, is 1 divided by the initial amount of chemical and the rate constant. So in this problem, you are told what the rate constant is, and you're provided with the initial concentration. So you should be able to simply substitute into this equation. Keep in mind that as a half-life, it's going to have time as, or some unit of time as the units of this answer. And those units will depend on the amount of, the units in the rate constant. So pay attention to that. Right? So let's wrap up. You're going to today combine crystal violet and hydroxide ion. It's going to start out as a very deep colored purple solution. Over time, this purple color will fade. So every 30 seconds to a minute, you're going to try to measure the absorbance of the solution. And then you're going to make a graph of the natural logarithm of those absorbances versus time so that you can figure out the order of the other reactant, actually, the hydroxide ion. When it's all said and done, you will have both the true rate constant K, and then you will know the order. Well, we already told you it's first order for crystal violet, and you'll know the order of hydroxide N. So when it's all said and done, you will write out a number here and a number here. So your rate law will be something like the rate equals 0.02. That's not the real rate constant, but 0.02 times crystal violet concentration raised to the first power times hydroxide ion concentration raised to whatever power you determine. That will be the final finished form of the rate law that you're after in this experiment. All right? Enjoy watching the colors change and fade. Take a large, robust data set. Again, the more data points you get, the better your graphs are going to be, and the more accurate your pseudo and ultimately real rate constant will be for this experiment. Good luck, enjoy your time in lab, and be safe. And I'll see you when we talk about next week's experiment in the next video. Have a good day.